I will try to readjust the mic so that it is in line with my band gap as well. All right. The next speaker for this session is Dr. or Professor Mario Santos from UWC, who is going to give us a talk on cosmology with radio telescopes, findings a needle in the data stack. Over to you, Professor.
Okay, thank you very much, and also thank you for the invitation. It's been great to get a bit outside my bubble and hear all these different science cases. I assume that I don't have any fellow astronomer or astrophysicist in the room here, probably not. But I assume everyone here heard a bit about cosmology and kind of what's going on with the universe in the news. So let me see if I can move this along. Is just the arrows here, or should I just space?
This one. Sorry, we just.
I'll just press space. All right.
Okay.
If it doesn't work, I'll keep pressing. All right. So yeah. So we're now in the era of really what I call precision cosmology, and so we have like a model that seems to fit the universe very well, and we get these really tiny error bars, but the parameters in that model still doesn't tell us about a lot of underlying science. So just to give you an idea, we still don't know what it is. About 70% of the energy in the universe, we call it dark energy. We don't really understand. We know some properties, don't really know what it is. There's another 25% that's called dark matter that, again, we don't have a lot of knowledge about. So what we really know in terms of energy in the universe is like 5%. So there's still a lot of work to be done. And in the future, the next few years, we'll be doing these three-dimensional maps throughout the universe, like this one you see here, where every single pixel there is a galaxy. And for that, well, we need to require simulations with very high dynamic range to go from stars to galaxies to all the universe. And also, we need extremely large and sensitive telescopes. So this is where observational cosmology comes in. Unfortunately, that means we need to know a bit of everything. So the idea, we start from theories with some set of parameters that we actually need to cycle through, run simulations that simulate the universe. We extract some observables from that. We need to add instrumental effects to it, and you then produce data mocks that will compare with the actual data. This form modeling is actually very complex and slow to run, so usually you make a shortcut where you kind of try to invert the data into some sort of observable that you can compare with our theories in a more direct, without going through this extra phase. But it is a complex system, and as I said, we do need some shortcuts. So as I said, we know in the area of precision cosmology, and what that means actually is that our signal now is actually, the noise is kind of below the signal, which was unusual until a few years ago. So that's great. But that means we actually are completely dominated by systematics. That's what I call the haystack here. We have lots and lots and lots of data to go through, but most of it is not what we want. And any small error in modeling these will leak into this signal here. And that's kind of the challenge of all the big surveys going on at the moment, all the satellites that we put into space to observe the universe. So this is where the Center for Radio Cosmology comes in at the University of Western Cape, where we try to combine all different sides, from simulations to theory to instrumentation, to put that all in one single group where you can interact and understand how these different problems can be solved. So specifically in terms of the use of high-performance computing, I'll say we're not like, we don't run, I'll say, extremely complex systems. The main language here is Python and C when we need speed. A lot of these simulations can be simplified to fast Fourier transform, so there's a lot of that going back and forth when you run these things. Sometimes if you run data analysis in the computer, then there'll be a lot of nonlinear minimization or using Markov chain Monte Carlo methods to probe the likelihood, the full parameter space. And lately, we've been looking more into the use of GPUs for neural networks. So those are kind of the main tools. So yeah, I can't go through everything, but I'll just give you two big examples that I think are relevant for what's going on in South Africa. One is trying to measure the structure of the universe across cosmic time using the radiation that's emitted by the tiny hydrogen atoms that exist throughout the universe. So this is using the neutral hydrogen 21 centimeter line. It's a very, very low energetic line. And that's the good thing about this is that we have hydrogen all across the universe from the very early days of existence of the universe all the way up to now. Now all the hydrogen is kind of inside galaxies, like you see over there. In Cosmology, we kind of zoom out and we have many, many galaxies make these maps. In the earlier universe, the hydrogen is actually everywhere, like in the intergalactic medium. And we observed that to trace the structure of the universe and then understand the composition and how it evolves and the underlying physics that drives the universe. So for that, in terms of data, so there's a theory side. From the data side, we are using the Meerkat telescope. I don't know if how many here have heard about it? A few, okay. So it's the largest radio telescope in the world at the moment that has been set up in South Africa. It's been running since 2018, and we're now expanding it to something that in a few years will be called the SKA. And there's many science cases for it. One of them is my science case in terms of measuring the neutral hydrogen. Yeah, just to point out where it is. It's in a low density population region in the Northern Cape, the Karoo Desert, next to a very small town called Carnarvon. You can visit it. It's, I think, you need to book a visit and make sure you don't bring your cell phone or keep it off, because otherwise you'll burn the system and you'll have to pay a few $1 million. So don't do that. But and don't ruin my observations. But yeah, it's a radio quiet area, so there's actually several instruments installed there, not just Meerkat. And yeah, I'm running these. I won't go through these details, but we've been running these large observations to map the universe using Meerkat. So the challenge here when we're trying to do that is, as I said, we have lots of other things complicating the measurement, and hence the title, needle in a haystack or in the data stack. We already have our signal, then you have just everything else in the universe, galaxies, all that stuff. And then you have our own galaxy, which is an extremely high contaminant. So, you can really see our galaxy here in the southern sky, and and actually it's a very hot emitter of radiation. And then you have instrumental effects that we also need to deal with, and all that can be parameterized, and so it's a large parameter set that you need to solve for all that. So one example is, from the simulation side is we need to understand these contaminants, so you run large simulations. Simulations that have been run at the CHPC, they do require lots of memory because you kind of need large volumes because it's the whole universe. So for instance, what you see here at the top is a simulation of what our own galaxy should be emitting in terms of galactic synchrotron emission. So it's radio emission at a few gigahertz. The other example is just the distribution of radio galaxies in the sky. But the problem here, as you see, you do running all these simulations. Our cosmological signal is a factor of 1,000, 10,000 times smaller than all these contaminants. So it's important to really understand these details and compare to data So we're still learning and comparing and to improve those simulations. In terms of removing those contaminants, another project that's been run with one of the students using UNets to train networks to try to disentangle between our very, very small cosmological signal and this huge contamination coming from our galaxy. And the network has been reasonably well outperforming this signal separation. I'll say it's something that requires more studies. So far, we actually been relying on simpler methods, principal component analysis or single value decompositions to take out these large contaminants. And back in 2023, you published the first cosmological result using Meerkat, where there was an actual detection of the signal using this method, where you start from something very strong and then you can clean it out and get back to our hydrogen signal that's being emitted throughout the universe for the past few billion years. So it's doable, but it's something that it's active research and using the CHPC. Yeah, another one is calibration and flagging, which is not so much, I'll say, an HPC problem, but it is computational intensive, how to fit for all the models of your all the parameters of your instrument. And then flagging, which basically means everything that you can't really explain that are outliers in your model. We need to be careful with that. But anyone, even if you don't know what this is, you kind of understand that there are these spikes here that shouldn't be really part of your data. And if you're wondering what you're seeing here, these are GPS satellites. So all the stuff you use to in your cell phone to know where you are, Google Maps, they're here and they're there, quite bad. And these things here is a cell phone tower that is like 50 kilometers from site, and it's quite bad for us. So we need to deal with that, and it's a very manual intensive process. So one thing we've been trying to explore is again using some neural networks, in particular UNet models, to see if we can make these more automatic. And here we have a comparison between our current semi-automatic algorithm flagging and the UNet model, which is performing reasonably well. And so it's another project from one of my PhD students. So yeah, I mean so this side is a lot of the HPC part has been mostly about generating these large simulations that you can use then in training our algorithms and so on, and a bit of it in this data analysis side of things. Now, where we've actually spent a lot of CHPC time has been in this second project, which I can summarize it's about trying to measure the temperature of the young universe. So, 13 billion years ago, what was going on in the early universe when the first stars started and the first galaxies formed, and how do you do that? So again, you run these simulations, and again, you do need a very high dynamic range, because a lot of the physical effects are happening at the star formation level, but we want to observe the whole universe, something that for which a galaxy is just like a very tiny dot, so it's the scales are huge. And you need to put all that together, and we've been running some, I'll say, not fully numerical, semi-numerical models, kind of try to speed up things. And there's been quite a few papers published using the CHPC simulations. And what you have here is more like a slice. The x-axis is time, so it's from, on the left is like the early universe, and then you keep going. This is age of the universe, when the universe is 10 million years, 100 million years, and so on until 1 billion years old. And you kind of can measure what hydrogen is doing in the universe at that time, and what you see here is kind of the temperature of that gas. Not just the temperature, but the ionization state of hydrogen. Hydrogen is an atom, can be ionized, and the reason why it's dark here is because it becomes fully ionized throughout the universe. And now the universe is like 13.7 billion years old. So yeah, we run this stuff, and you know, it works. It is still a bit slow, but because you want to run that many times, if you just run it once, it's actually okay. So I've been playing a bit with emulators, ways to accelerate that. Again, from a project from another student where, again, using UNets, we try to go straight from, say, the seeds straight to the final maps without going through this, you know, physical process in between. And again, it has performed quite well. She presented in 2023 this work at the ICLR. So I think that was quite interesting. Now, I told you about Meerkat, which we're using to measure hydrogen emission and measure the universe in the latest stages of evolution. When we want to observe the universe when it's very young, you know, from very far away, then we use another instrument called Hera, which is also installed near the Meerkat site. You see the two here from, this is an early photograph. If you go to Google Maps now, Google Earth, you can actually see the full telescope there. This is working at very low radio frequencies, around 100 megahertz, so it's the FM band that you can listen to in your radio. So part of that is a cosmological signal. Yep. And yeah, those are the dishes, kind of weird shaped. They're big, you know, I wish I had a person next to it, but yeah, they're like 14 meter in diameter. And we're using them, again, it's set in South Africa. You know, one of the biggest huge of the CHPC has been this. As I said, these you know, simulations, they are reasonably fast because they are semi-numerical, but you need to run them a lot because you have lots of cosmological parameters that we need to change, astrophysical parameters. And what you see here were simulations run as CHPC, where you see the different quantities like the temperature of the gas, the ionization state, and so on, and how they change as you change different parameters. So if I go back, and again, it becomes easier to see that effect. And so yeah, you kind of want to play with all that and then compare with your data, which is what you're observing with Hera. So it's been mostly Monte Carlo type of parameter exploration that we're using. And this is just, you don't need to you know, go through that, but just to give you an idea at the end, once you start comparing with the data, you end up with these corner plots, you know, these ellipses, constraining your parameters. I think this used kind of about 10 million CPU hours at the CHPC. And you know, this was actually around, so Hera, Meerkat is a fully led South African experiment. Hera is actually US led, but this stuff was actually run here in Cape Town, and you know, the conclusion, I don't expect you to, well, learn about the details, but the interesting fact was that this was the first time that we were able to constrain the temperature of the universe. And at least we know that 13 billion years ago, the universe was hotter than 500 Kelvin, which was actually the first time this was kind of measured. It might be hotter, so we still, you know, the distribution is still a bit wide. We want to improve on that, and there's more observations ongoing and more simulations of perimeter filters going on with this HPC. So yeah, final thoughts. I hope I kind of convince you, even if you don't care much about cosmology, that there's quite a bit of observations going on at radio wavelengths from South Africa, and there is, you know, the data volumes are absolutely huge. So it is an issue how well I can move data around and analyze it. We're moving towards something I would call full forward modeling, where we run simulations and do the data fitting together at the same time without any back and forth. It does require a lot of parameter fitting, which is very computationally intensive. And we want to do that here in South Africa. I mean, the data should be here. We shouldn't be shipping that somewhere else in the world. And part of this was done at HPC, in particular those you know, more computing intensive simulations. Now, I would say my work is not purely a standard HPC problem. Yes, we use CPUs, they are great. And sometimes we have peak use of CPUs, we just deploy things and get going, and that's great. But there's a lot of time where we're playing with storage. Even the simulations produce vast amounts of data. We do need sometimes massive amounts of memory. GPUs are a big issue. We don't have enough of them around. And the reality is that a lot of students in my group do require this user support to install software and do code optimization that unfortunately I probably don't have that expertise inside our group. So that interaction is also very important. So I'll stop here. Thank you.